Welcome to the video that I'm going to put together here on inverse relations of functions. Basically what an inverse is a function that undoes the work of another function. So for example, the function f takes the point x to y. Well, the inverse will take the point y back to point x. So essentially it's your function goes this way, right? Takes some ordered pair x, turns into an ordered pair y. The inverse function is a function that basically undoes that process. Now, it has to work for every single ordered pair. You can't find a function say, oh, it works for this one, but then you try another ordered pair on the relation and it doesn't work. So that's important. That it has to be a process or a rule that will work for every single ordered pair. One thing to note here, we do use this symbol f to the negative 1, which means the inverse of f of x. It does not mean, like we do if I have w to the negative 1, just a generic w to the negative 1 with laws of exponents, that means w over the 1 over w to the 1. W to the negative 3 is 1 over w to the 3. Negative 1 put here in function notation. So again, it comes down to context, how and where it's used. It becomes important you realize that that exponent situated there does not mean 1 over f of x, which sometimes students mistakenly think that it means. Now, not all functions will have an inverse. So you remember we said it has to work for every point on the function. So for example, if I had this graph and I had these 2 points, let's say this was 1, 2, 3, this was 4, and this was 2. So this was the point 2, 4. This was the point negative 2, 4. Well, the dilemma here would be, so when x is equal to 2, I can clearly see, 2, I can see that the y value would be 4. I can see that if x was negative 2, the y value would also be 4. The problem would be if we said, oh yeah, well, let's try and go the other way. When y equals 2, what point does that work back to on our x? Well, the problem would be there's multiple answers. So this would be an example of a function that does not have an inverse for that reason, because it has more than one x value for a particular y value. Now there's a special name for that type of function. So this function here is an example of a function that doesn't have an inverse. In order for a function to have an inverse, we say it must be 1 to 1. 1 to 1. A 1 to 1 function is a function that for every x, there is only one y, and for every y, there is only one x. So here's an example of a function that, given some y value here, well, the problem would be there's multiple x's with the same y value. So we have a nice, easy way to test this from a graph. You may recall from grade 10, NERF studies, if you were testing this graph for a function, you learned something called the vertical line test. And a vertical line test was simply, if you can draw a vertical line that only cuts a graph in one place, it is a function. So this graph is a function. The inverse test, which is to see if there's only one y for every x, you can probably maybe see where this is going, is what's called a horizontal line test. Right? So for example, if I draw a horizontal line and it cuts the graph here and here, that means that there are multiple x's for a particular y. So this is an example of what they call a many-to-one function. It's not 1 to 1 because it failed the horizontal line test. All right, so the horizontal line test checks to see if a function has an inverse and see if it's 1 to 1. So this would be an example of a function that I could not come up with one single rule that would get every point, every x value mapped back, or sorry, every y value turned back into a particular x value because there's more than one x for given y's. Now looking at some of the notation and some terminology that goes with this. So we've already talked about this. If you have the inverse of y equals x, that's telling me that f evaluated at x gives me the y. So essentially, in this, what it's telling us is when you go from function to inverse or inverse to function, I have it down here, it says in plain simple English. If you remember nothing out of this section on inverses other than this, the x and y coordinates just switch places. That's what happens. Now in order for that to happen, you can only have a single ordered pair that has a particular x and also a particular y. So it has to be a one-to-one function. Another thing worth noting is that when you do take the inverse, so it's saying here the domain of the inverse becomes the range of the function. The range of the inverse becomes the domain of the function. Well, that kind of falls right in line here because hopefully when you hear the word domain, your brain is triggered to think x values, and range, your brain is programmed to think y values. And given that the inverse is a rule to switch the x's and the y's, that's why your domain and range switch from inverse to function. Now, how does this play out visually on a graph? Let's suppose I looked at these graphs that I have down below here. Now, basically, if I wanted to sketch what I thought the inverse of this looked like, I would do it like I said up above. I would switch all the x's and y's. So, for example, this ordered pair right now is -5, 3. Well, on the inverse, it should become 3, -5, over 3, down to -5. Unfortunately, that's going to be down here somewhere. This point, which is at -3, -2, should now be found at -2, -3. -2, -3. So that point will be there. Which ones have it done? That one went there. This one, which is at -2 and -1, would be at -1 and -2. That one would be there. This one, which is at 0, 4, would end up at 4, 0. This point, which is at 3, 3, would not move, because when you switch x and y, it would stay the same. Now I'm going to connect these in the order that, so I started here and I'm kind of trying to go around this, so let's connect them in that order. So I went there, to there, to there, to there. Didn't do that one very well. Then I went over to here, and then this one stayed the same. Now, knowing what you know about reflections, you should recognize that there is a mirror image here. Now, it's not across this line, it's not across this line, so it's not a horizontal across the y-axis or a vertical across the x-axis reflection. I'm going to put a line here. This is an important line that we would expect students to recognize. It's called the y equals x line. The y equals x line is, think about if y and x are equal to each other. So it goes through 1, 1, 2, 2, 3, 3, 4, 4. And when you reflect an inverse, or when you come up with your inverse, what happens is your points reflect across the y equals x line. So if you look at the red graph, I know it's not a perfect rendition of this, but freehand, you can kind of get the idea that the line of reflection was this diagonal line here, y equals x. So the line y equals x becomes the line of symmetry for inverses, which is why this point, which was at 3, 3, stayed there, because it was on the line of reflection. I don't know if any of you were looking at this and saying, wait a second, this graph doesn't even really have a function. And it is true. This function is not one-to-one, because if I drew a horizontal line across here, I would cut the graph in more than one place. So it's actually not one-to-one. Now, I can always visually represent an inverse, but what it means is I can't come up with a mathematical single function that would turn this function into this function. It would take multiple functions doing multiple things in different places, which would be an example of a piecewise. Now, the good news for you is we don't actually have to figure out those functions. We just have to realize when there is an inverse and when there is not an inverse. So this is an example where visually this is what it would look like. I have my reflection, but because it is not one-to-one, there is no actual inverse function that would exist for this. If I take a look at this one, just pick a couple of points. So remember this one is 1, 2, so 3, comma 0 should become 0, comma 3. I don't know, this point looks like if x was 7, so 1, 2, 3, 4, 5, 6, 7. That one right there is at 7, comma 2. Now you say, how do you know that? I can see, you probably can't maybe make it out here. I can see that I typed this in square root x minus 3. So I know that if I put x as 7, 7 minus 3 is 4, the square root of 4 is 2. So I know that 7, 2. Well, that means that 2, comma 7 should be on the inverse. 1, 2, 3, 4, 5, 6, 7 over 2. 7 over 2, right about there. So that's probably enough to kind of get it. These don't have to be perfect, but you get that. I'm just going to put my line of reflection in and see what it looks like. That would be your y equals x line. So it goes right up here and it cuts it at a 45-degree angle. So these two should both be 45 and the same size. And that looks like a reasonable sketch of what would happen. Now this one is a function, right? Passes vertical line and it passes horizontal line. So this one would be able to have a single inverse function to turn this graph into that graph. So at quick glance, this is not one-to-one. It's many-to-one. Fails horizontal line test basically everywhere. So there's no mathematical single function that could turn this into its inverse. But if we wanted to visually look at what would be the functions required to get your inverse, let's start by going negative 3 and 7. So that should be over here. So 2, 4. I'm just going to fudge it a little bit. So 7, negative 3 would be down here. I've got negative 1, comma 3, so 3, negative 1 should be a point. I've got negative 5 and 3, so 3, negative 5 should also be a point. Should be right about here. So if I draw that, put my line of reflection in. So if we were to fold that graph along that line, y equals x, it would look something like that. But again, as we said, it is not one-to-one. Therefore, there is no single inverse function to turn this graph into this graph going this way. It would take multiple functions. All right, so let's just look at how we kind of play with this graphically, or sorry, algebraically. So essentially this is saying find the inverse of each of these functions. So let's pick b. We won't do all of these ones. Let's pick b. So my function is 1/2 of x plus 5. And I would like to find the inverse function. Knowing what you know, hopefully about mathematics and symbols and function notation, f of x is fancy notation for y. So there's your y, that whole left side, and obviously there's your x. Remember, the strategy to determine inverses is simply this statement. Switch your x and your y. So I'm going to take this graph and I'm going to, instead of putting y here, no, I'm not going to use f of x. We'll come back to that in a second. So I'm going to, instead of f of x, I'm going to put x, 1/2, and I'm just going to put here, just to put a y, plus 5. So I switch x and y, and then you rearrange for the new y. So you have to formula rearrange, like you would do in science or physics or obviously in math. So I'm going to double everything. 2x equals y plus So you're going to multiply everything by 2, not just the one with the fraction. So this would be y plus 10. I'm going to bring my 10 over. I'm going to, there I have my y. So y, now we're going to switch notations out to the right notation. What's the symbol? So this is the inverse. Instead of y, we're going to swap it out for the correct notation, f to the negative 1 of x. So there's your inverse notation. It is important you write this out to show you know the notation. The inverse is equal to 2x, subtract 10. If you notice the original function, notice what we were doing. We were taking, what did I mess up here? Something's wrong. X, 2x, y, plus 10. No, it's all good. Yeah, I don't know why this 10 was throwing me off, but we're all good. So my math is fine. I don't know if I've got, oops, I didn't want to jump ahead that quick. Let's do another, I don't know, let's take d, I guess. So d is the function f of x is equal to 8x plus 12 over 4. Now this actually would simplify before I even start, but let's pretend we didn't see that. Let's just do our generic switch x and y. So this will become x equals 8y plus 12 over 4. So multiply both sides by 4. 4x is 8y plus 12. Subtract 12 from both sides. And now to isolate the y, we're going to divide each term by 8. And that gets us 2. So y equals 1/2 of x. 12 over 8 would be 3 over 2. Switch out to proper notation for inverse. So this is now the inverse function. 1/2 x minus 3 over 2. What this means is if I graphed this function and then I graphed this new function, this would be the mirror image of my original function on a graph through the line y equals x. Now if we pick one that's a little more challenging, let's suppose I had something like this and I wanted to, so that's a linear one, we already did a couple of those. Let's try this one that's got a square root in it. Same procedure, switch, instead of f of x, that's my y, I'm going to make it an x, square root, y take away 3 plus 4. So move your 4 over, x take away 4, square root, y minus 3. Now I need to isolate the y, so I have to get rid of that squared, or square root by doing the opposite. X subtract 4, all squared, will equal y subtract 3. So then y must equal, I got to add 3 to both sides. X subtract 4 all squared plus 3. Swap out to your correct notation. Inverse function is x minus 4 all squared plus 3. Now, just to look at how I could throw this into the mix with, I don't think I have an example, I'm just going to make one up here. Let's suppose we've got g of x is negative 4 f at 2x minus 6 plus 5, and then I say given negative 6 comma 2 is on f of x, where is this ordered pair on the the inverse of g of x. So here's what you would remember. The connection between g of x and the inverse of g of x is to switch the x and y coordinates. So seeing the inverse, what I do is I ignore that first, and I map this point, negative 6, 2, which is on f of x, and then I'm going to do all this stuff to function f to turn it into g. So I will map that point to g of x. After I get that new point on g of x, then I will switch the x and y. So what students will do wrong here is they'll switch the x and the y first. You switch it at the end. So you're going to go g of x is equal to negative 4 f. Remember, we have to factor this out. Minus 3 plus 5. So my mapping rule to get from f to g would be take half your x's, go right 3, multiply your y's by negative 4, and then add 5. Let's take our ordered pair, negative 6, 2, and map it. So negative 6, 2 would be 1/2 of negative 6 plus 3, negative 4 times the y value, plus 5. That's 0, negative 3. Now this would be where it is on g of x. Therefore, on the inverse of g, you simply reverse your ordered pair. There's where it would fall on the inverse. All right, so that's how you tie inverse functions in with our function work we've been doing up until now involving transformations. And I've also shown you visually how to identify what an inverse would look like. And in addition to that, we have discussed how to algebraically determine the inverse function to turn one function into its new function, or its inverse function. So those would be kind of the skill sets that we want you to be able to pick up on this section. All right, so that's all I've got for inverses, and that's just kind of a scratch at the surface so that you know what they are, and kind of it's a new term and symbol that you've now been exposed to. So hopefully you'll be able to do some of the practice questions that I'm going to post to go with these. If you run into any problems, as always, just let me know and we'll get you pointed in the right direction. Thanks for watching. Best of luck.